So today we're going to talk about the fifth section of our unit on chemical composition called Empirical Formula. Okay, so we're going to talk about how to take grams and calculate the formula of a compound. This is basically the opposite of mass percent, where we took the compound and we broke it up into grams, and we're going to go the opposite direction. So we're going to use masses of elements to determine the chemical formula. And that chemical formula represents a ratio of the number of atoms of each type of element in a compound. And so basically what we're going to try to do is get things into either atoms or moles and then use that to determine our ratio. Okay, so we have a mystery compound. It says a 0.2015 gram sample of the mystery compound contains 0.0806 grams of carbon, 0.01353 grams of hydrogen, and 0.1074 grams of oxygen, and we want to know the chemical formula. Well, first we need to convert to moles. Now, we just talked about how it was a ratio of the number of atoms, but to go from moles to atoms involves Avogadro's number, and this relates to any element. So basically what we're doing is, instead of converting all of these to atoms, we're taking out this step, because since it applies to all elements the same, and we're just going to stop at converting to moles. We're taking out an additional step. Makes things a little easier. Once we get the number of moles for each element, then we're going to divide by the smallest one in order to get a ratio. So we're trying to relate all of the moles of all of our elements to each other. So first, let's convert to moles. So we're given this 0.2015 gram sample, but really what we're interested in is the masses of each element. And so let's start with carbon. So we have 0.0806 grams of carbon. Well, if you remember from previous sections, the way to go from grams to moles is molar mass, or atomic mass if it's an element. So based on the periodic table, we know for every 1 mole of carbon, there are 12.01 grams of carbon. And so if we divide, we end up with 0.00671 moles of carbon. Okay, so this is step 1. We're going to do the same thing for hydrogen and oxygen. So 0.01353 grams of hydrogen. And if we convert that one, we get for every 1 mole of hydrogen, we know from the periodic table, there are 1.008 grams of hydrogen. So again, if I divide that, I get 0.0134 moles of hydrogen. Let's do the same thing with oxygen. We have 0.1074 grams of oxygen. Using the atomic mass from the periodic table, I know for every 1 mole of oxygen, there's 16 grams of oxygen. And if I divide that one, I get 0.00671 moles of oxygen. Couple things here. I'm rounding, I'm giving myself about 3 non-zero digits. Don't round too quickly, because you need some of those extra numbers for the next step, which is to divide by the smallest to get the ratio. So I would go about 3 non-zero integers out, wherever that happens to be. Okay, so now we're going to divide by whichever one is the smallest, and that's how we're going to relate all 3 of these elements to each other. And so it just so happens that carbon and oxygen both have the smallest number of moles, so it really doesn't matter which one we pick. We're going to divide all 3 by the smallest one. Again, this is how we're relating them all to each other, because that's what empirical formula is. It's a ratio of the number of moles of all the elements. Well, since we're dividing one number by itself, this is equal to 1. 0.0134 divided by 0.00671 comes out to 1.99. And again, dividing it by itself, so that comes out to 1. This is very, very, very close to 2, so we can just round it to 2. And so now that gives us our ratio. So to write our empirical formula, we have C. We don't put the 1. Remember, if the subscript's a 1, we don't write it. H2O. And that is our empirical formula. That's the ratio of the number of moles or number of atoms of each element in the compound. So CH2O. Okay. Well, is this the true formula? Is this how this compound exists in nature? It could be CH2O, which is our empirical formula, But we can also take that 1 to 2 to 1 ratio and multiply it by whatever number we want. So if we take our 1 to 2 to 1 ratio and multiply by 2, we get C2H4O2. Or we could multiply it by 6 and get C6H12O6. And so there could be multiple combinations like this. And so we need to figure out which one is the actual formula and which one is what's called the simplest formula. Okay, well there are two kinds of formulas. The first one is the empirical formula. This is the simplest whole number ratio. This is what we calculated, our 1 to 2 to 1 ratio. It expresses the smallest whole number ratio of the atoms present. So our CH2O is an example of that. The other type of formula is the molecular formula. This is the real formula. This is how it exists in nature. And for CH2O, the real formula, or the molecular formula, is C6H12O6. So it gives the actual composition of atoms present. Notice that the ratio is the same. It's still 1 to 2 to 1. It's just not the simplest ratio anymore. Now, sometimes you can have where the empirical formula and the molecular formula are equal. For example, let's say if we had H2O. It's a ratio of 2 to 1. This is the simplest whole number ratio, but it's also the real or the actual. And so in this case, empirical and molecular are the same. Okay, let's do another example of how to calculate empirical formula. So let's say we're going to make nickel oxide from nickel. That means that we would be burning it, so we're reacting it with oxygen. Say we start with 0.2636 grams of nickel, and at the end of our reaction, we have 0.3354 grams of nickel oxide. Well, we know we have the nickel we started with. We know we reacted it with oxygen, and so that extra mass in our product, our nickel oxide, must be from oxygen. So to find the amount of oxygen, we take the total product minus our nickel. So here's our nickel oxide, and here's our nickel, and that gives us our grams of oxygen. So if we want to find the empirical formula for nickel oxide, or the ratio of the number of moles of nickel to oxygen, then we need to do a few steps. The first thing is to find the mass, or the grams, of each element. We were given the grams of nickel, we subtracted to get the grams of oxygen, so we have both of those. Then we need to determine the number of moles of each, because remember, that's how we're going to compare elements to each other to get our ratio, is by converting them to moles. Because originally we would convert them to atoms, but we're taking out the Avogadro's number step and stopping at moles. Once we have the moles of each element, we can find our ratio, relate them to each other by dividing by the smallest number of moles, and then we're going to round them to whole numbers. Now, the last example we did, we came out to 1.99 for hydrogen, and that easily rounded to 2. But if you don't get whole numbers, let's say you get 3, let's say we were doing our previous problem, and we got 1, 1.5 for hydrogen, and 1 for oxygen. Well, 1.5 isn't close enough to round, and you can't have half a mole of an element. So we need to multiply all of our ratios by some integer in order to convert them to whole numbers. If you're not sure what integer would work, start with 2 and keep working your way through until you get one that works. I know that 1.5 times 2 is 3. Oh, there we go. And so I'm going to multiply by 2. But if I multiply this ratio by 2, I have to multiply them all by 2. And so now that ends up with a ratio of 2 to 3 to 2. Okay, so keep that in mind. If you happen to get a ratio that is not close to a whole number, then you need to multiply by these integers until you get a whole number. Okay, so let's look at our formula for nickel oxide. And so if you remember from the problem, we had 0.2636 grams of nickel, and we also had 0.0718 grams of oxygen. So our first step was to get mass. Check, we got that. Now we need to convert to moles, and so we're going to use atomic mass in order to do that, because that's going to relate grams to moles. And so for nickel, our atomic mass, based on the periodic table, is 58.69 grams in 1 mole of nickel. And if we divide that out, we end up with 0.00449 moles of nickel. Let's do the same process to oxygen. We're going to use oxygen's atomic mass, which is 16 grams in 1 mole. And if we divide that out, we end up with, weirdly enough, the same thing. But that's okay, because that's actually good. So really, they're both the smallest, so we can just divide by 0.449, because remember, this is step 3, to divide by the smallest to get that ratio. And so we're going to end up with 1 and 1, and so that means that our empirical formula is NiO. Remember, if the subscript is a 1, and that's basically what these are, it's that ratio, it's that subscript, then you don't write them. Okay, so here's what I would like you to try. Find the empirical formula for an oxide of aluminum. Oxide just means that it contains oxygen. So I've given you the grams of each reactant. Okay, make sure you convert your grams to moles. Divide by the smallest to get the ratio. If you end up with a ratio that is not a whole number, which, hint, hint, you will, okay, it will not be a whole number, then you need to decide what integer to multiply all your ratios by in order to get whole numbers. Okay, so try that. This should be your answer, but pause the video, try it on your own, okay, and then we will go over it together as a class. Okay, so make sure you pause the video for now, but I'm going to go on to the next slide. Okay, we have one other way to calculate empirical formula, and this is based on percent composition, which we just talked about in the previous section. So let's say we have these percents by mass of the 4 following elements: platinum, nitrogen, hydrogen, and chlorine. This compound composed of these 4 elements is called cisplatin. It's just the common name. Now, we know that step 1 is to get masses, and right now we are in percents. Well, the easiest way to convert percents to grams is to assume 100 grams of the total. Because if we take a percent times the 100, it just comes out to that number. Now, you could assume any number of grams total that you wanted. You could say 1 gram, 50 million, 1.23. It doesn't really matter. But because 100 is related to percents, this is a really easy conversion. So if we assume 100 grams total, then that means that we have 65.02 grams of platinum. We have 9.34 grams of nitrogen, 3.02 grams of hydrogen, and 23.63 grams of chlorine. Okay, so we've got our first step out of the way. We found the masses of all our elements. Now the second step is to convert to moles, because that's how we're going to compare all of our elements to each other. And we know that the way to convert between grams to moles is to use atomic mass, which we can find on the periodic table. So for platinum's atomic mass is 195.1 for every 1 mole. Okay, and I'm just going to go through and write all these out for all of my atomic masses. Nitrogen, I know, has an atomic mass of 14.01 grams in 1 mole. Hydrogen's atomic mass is 1.008 grams for every 1 mole. Oh, and that's not carbon, that's chlorine. And chlorine has an atomic mass of 35.45 grams for every 1 mole. Okay, now I just need to do a little bit of math and divide all of these. So if I do my platinum, I get 0.333 moles of platinum. For nitrogen, I end up with 0.666. Okay, and what you could do is pause the video and do these on your own, and then follow along and check and make sure that you're getting them correct. If I take hydrogen, I get really close to 3. And I probably should have a few more digits. So let's just check that one real quick. We have 3.02 divided by 1.008. 2.996. I like that better. Let's do that. And then for chlorine, we're going to get 0.666. Moles and moles. Okay, so that's step 2. We've converted everything to moles. Now the third step is to develop our ratio. So we need to divide all of these by the smallest, and that happens to be 0.333. So I'm going to divide them all by the smallest number of moles in order to get my ratio and relate them all to each other. Okay, well, I know this is going to come out to 1. This comes out very close to 2. 2.996, or 3 divided by 0.333 gives me very close to 9. and this one gives me very close to 2. And so my empirical formula, and you can just write your elements in the order that they're given in the problem, would be platinum, no subscript because it's a 1, then N2H9Cl2. Okay, so make sure you try that previous example if you haven't already, and we'll go over it in class. Have a good day.